So this is question 34. Um, Absolute value, right? Absolute value inequality, right? So that tells us that we have to look at um, the situation where we have that type of inequality symbol. Remember, if the inequality, the absolute value comes first, you read it as a less than 3, right? And absolute value less than something provides you this rule. If I start with ax plus b is less than c, the rule then becomes the opposite of c, so you take that number, multiply by -1, throw in that same symbol, and then you have ax plus b is less than c. Okay? So ultimately, the right-hand side of that, okay, if I erase that, the right-hand side is exactly what we started with, right? And we just introduced then the less than negative c on the left-hand side. So it gives you that between statement. The smart board's not wanting to cooperate today. I don't know what the deal is. So same thing here. We're going to take x minus 1 over 2 is less than 3, but it is also greater than negative 3. Okay, that's how we read it. We're going to read this several different ways. You can say negative 3 is less than x minus 1 over 2, which is less than 3. Okay, so kind of using your transitive property is that this number's in the middle, right? This number is less than that number, and this number is less than that number. Does that make sense? Okay. Or you can read it from the middle and then move your way out. X minus 1 over 2 is greater than negative 3, or x minus 1 over 2 is less than 3. Not or, but and. Does that make sense? All right, so a couple different ways you read that. But now let's think about this. If you had just that, what would you do first? Multiply both sides by 2. What if you had just that? Multiply both sides by 2 again, right? Okay. So when we see what I mean? It doesn't want to work. It might have something to do with the idiot that's operating. You're not. So we get that 3. That sounded kind of like maybe you are. You would multiply all parts by 2, right? Okay, so multiplying everything by 2, and we get negative 6 is less than x minus 1 less than 6. Okay. Now, if I just had, that part, you would add 1 to both sides, right? If I just had that part, I would add 1 to both sides, right? So let's just add 1 to all 3 parts. So adding 1, I'll get negative 5 less than x less than 7. So now what we want to do, the assignment asks you to type your answer in interval notation. Okay. Well, the Word gives it to us in set notation. So we have to transfer this, and hopefully if you've got it like this, negative 5 is less than x is less than 7, it's pretty easy. We go negative 5, comma 7, because they're both less than signs, they're both parentheses. Because we're going to exclude negative 5 and exclude 7. But if you're unsure about yourself and you want to make sure that you are doing this correct, okay, you should be able to take any number in this interval, okay, any number in that interval, and plug it in. You should get a true statement. So if I show, choosing, now I'm going to maybe negative 3. Negative 3 minus 1 would be negative 4, right? Negative 4 divided by 2 would be negative 2, right? Absolute value of negative 2 is 2. Is 2 less than 3? Yeah, okay. And every other number I choose out of there should give me a similar result. Try 0. 0 minus 1 is negative 1. Negative 1 over 2. Absolute value of that is negative, or is positive 1/2. Is 1/2 less than 3? Yeah. So you should be able to go through all those, and I know there's an infinite number of them, but picking a couple of them that might convince you that you're on the right track. Now, if you pick out a number, I'll get your question in a minute. If you pick a number that's out of that range, say like 9. 9 is out of there, right? If I go 9 minus 1 is 8. 8 divided by 2 is 4. Absolute value of 4 is 4. Is 4 less than 3? No, that's a false statement, and that's why 9 wasn't in this solution. Okay? So that's what I like to do. I like to pick a couple numbers that are in that range to make sure that maybe I got a good idea that I am right, but I also like to pick out a couple numbers that are outside the range just to kind of reassure myself even more. Okay? Right? Yeah, because we want this to mimic a number line. So if I put a number line in here, if I'm traveling left to right, we're going to come across -5 first and then 7. Because there's going to be some other things that we do with that we're going to want it in that number line format. Good question. Other questions? Yeah, which one? 35? As a student, you guys probably don't like questions like this, because I remember when I was in Mrs. Cole's class, she'd do this all the time. We would do stuff in class, do all the number stuff, calculations, and always get like concrete answers back. Some of us were clever and we'd use our calculator to kind of beat the system. But then on tests and quizzes, she'd give something like this, which eliminated the calculator, right? But we're going to approach it the same way. Remember the A and D here are just representing values. Okay, so let's say if I had the idea that X, let's just say A was 3 and D was 10. Okay, would we know that we're going to rewrite this as X minus 3 is less than 10 is less than -10? Would we be able to do that? Okay, so let's think about it this way. A with 3, we changed to 3, changed to 3. D, we changed it to 10, changed it to 10. So wouldn't this over here be negative D? Is that going to make sense? And this would be still A. So that's kind of the approach here, is that we're still viewing that as a number and that as a number. So when we rewrite this, we're going to go X minus A is less than D, but X minus A is greater than negative D. So now we're going to add, I'm going to solve for X again, so we're going to add A to both sides, or all three sides, I guess. Add A here, add A there, add A there. So I get negative D plus A here is less than X, is less than D plus A. And however you write A minus D on the left, or A plus D on the right, doesn't really matter, okay, because of the commutative property. But that's the set notation that we have. If we put this in interval notation, think about this being a number line. We know that this number here, because I have the opposite D plus A, that has to be a smaller number than positive D plus A, doesn't it? So this number is first. So opposite D plus A, comma, D plus A. And that's how you're going to write that interval notation. If you wrote it, like I said, you went A minus D, and either D plus A or A plus D again, doesn't matter. Both those should be accepted by the website. But I'm just trying to get you to remember, regardless of what numbers you use, A can be anything, D can be anything. What is the process? And that's showing you the process. Does that make sense? Okay. Last class asked about 10 too. Let's see here. Nope. All right, so last class they asked about 10 with that one. So why don't you give me your, it's an X to the 4/3 and 2/3 in the middle. But what are your, let me write this up. We got X to the 4/3, X to the 2/3. What was your coefficient that went here? -8, and what was your constant? +50. Okay. Just so we get, I didn't want, mine's the same one as last year, so I didn't want to do the same one on film. I want you guys to have multiple examples of stuff. Couple different ways we can think about this. I think the best way this is not a polynomial equation. It's got those exponents of fractions, okay, or rational exponents, usually what we call it. But if we look at them, is that exponent right there and that exponent right there, are they in a 2-to-1 relationship to one another? Okay, so that's the key thing to think about. When we're solve this equation, okay, that 4/3 and that 2/3 scares a lot of people. But if you recognize that they're in a 2-to-1 relationship, we can make this problem a little bit easier, okay? If they're in a 2-to-1 relationship, all you have to do is say that thing, I'm gonna bring in an arbitrary value, arbitrary variable, okay? I use U a lot. I think WebSign was using like a capital W or something like that. It doesn't matter, but I'm gonna let U be that variable in that exponent. So x to 2/3, okay? And because I know then that these two things are in a 1-to-2 relationship or a 2-to-1 relationship, I know that that's going to make that 4/3 a little bit easier to deal with, okay? But just to show that algebra of why this works, if I have U equals x to 2/3, then U squared should be x to 2/3 squared, shouldn't it? And doesn't that evaluate to x to 4/3 or a simplified x to 4/3? Does that make sense? So that allows me, hopefully that shows you, you don't have to do this part every time, because if they're in a 2-to-1 relationship, that will always happen. Okay, what I got in the box here. But it shows you that you can take x to 4/3 now, and you should be able to rewrite it as U squared. So we'll rewrite this equation as U squared first, okay? Minus my 8. But now x to 2/3, you should be able to say, okay, well, that's the same thing as U. So U, and then plus 15 equals 0, okay? Hopefully, question 9 and 8, I think maybe hope at some stage walk you through one of these problems to help you get to this stage. Once we're here, not too bad to factor, right? U minus 3, U minus 5. You guys agree with that? Okay. So U is 3, U is 5. U equals 3, U equals 5. And I think now the hard part is realizing that we have to back substitute. Okay, so U, remember we let U be x to 2/3. So I'm going to substitute that back in with x to 2/3 and set that equal to 3. Okay, same thing here. I go x to 2/3 is equal to 5. All right, and now we get to a stage, and we'll talk about this a lot more when we get to the next chapter. Okay, I get confused a lot in the next chapter. But you did talk about this in Algebra 2 and how I address this. Okay, we want to solve for x to the first, right? Okay, so that's a problem provided what we have right now. We have x to 2/3. How can I make that exponent go to 1? Multiply by the reciprocal. Okay, and I'm not going to multiply by the reciprocal. I'm going to raise this whole side 2 3/2 to that reciprocal, and now I'm going to multiply power to a power, right? That's the actual principle that we're going through here. Because now a power to a power, that does mean we multiply. And because those two things are reciprocals, that's going to give you 1 as an exponent. So I get x to the first here. Okay. Now the same thing is going to happen to the right-hand side. I got to raise that 3 to the 3/2. And this is what I was talking about in Algebra 2. What does 3 to the 3/2 mean? Okay. Well, whenever you have x, some value, don't care what it is. Let's not use x. Let's use a. Some value a, and I raise it to some rational exponent. Some exponent as a fraction, right? Okay. That is exactly the same thing as saying that I'm going to take some root of a. We're going to figure out which root that is. And it's very easy to determine this, as long as you remember that that denominator becomes the index out here that you're taking the root of. Okay? So that'd be the square root, cube root, fourth root, whatever. And this m, the numerator, is actually the power of a. Okay? Now, I don't really remember it that way. I don't remember as a raised to m over n equals n, the nth root of a to the n. I remember this. I know that if I had something like 9 raised to the 1/2, okay, I know 9, I just always in my mind said, I know 9 raised to the 1/2 is equal to 3. I know that fact, okay? So then how can I rewrite this as a root so that I get 3? Well, 9 has to be underneath, right? And it has to be 9 to what power? The first power, right? No other way I'm going to get 9 to go down to 3 through using roots, unless it's got a power of 1, okay? And then where does that leave the other number to go? Out front, right? Okay? So if I can do that with 9, I can see the pattern that the numerator went there, and the denominator went out there, okay? I think it's a little bit easier than to, when I come across 9 to the 2/3 or 9 to the 5/4 or something like that, where I can position the 5 and the 4, the 2 and the 3. Does that make sense? Okay. So coming back up, I guess, see if we can draw a comparison to that. Okay, with 3 raised to the 3/2. Okay. Well, if this was 1/2, I know that that 2 would be out front, and the 1 would be with the number on the inside, right? But now the number that goes with the radicand is that 3. So what is 3 raised to the 3rd power? Three times 3 is 9, times 3 again is 27, right? So square root of 27. Okay. Now I got to do the same thing over here. X. Take 5, raise it to the 3/2 power. Okay. So now x is going to equal, bring the square root out, or make the square root. Okay. And now I got 5 to the 3rd, right? Now I have the square root of 125. That gives me 5 radical 5. And those are my 2 solutions. Make sense? There's another way of doing it. Let's do it this way. Let's go. Because that rational exponent process might cause issues for some people. So let's say I'm just going to delete everything and say we start back with, and I won't delete it. What's going on here? Let's go to your page. Let's say I started with x to the 2/3 is equal to our 5. Okay? I don't like that 2/3, so can I do this? Does this make sense to us? Because now that's going to give me what over here? X squared, and it gives you what over here? Now what can I do? And that might, if you forget your rational power principle, the rational exponent principle, you can do that route. I don't know if I put plus or minus in class. But that's necessary. Is that helpful? Any others? 8. I think the last class had that one, so let me get the format here real quick. And yep. Give me. All right, so. What do you have right here? Seriously? I had. What was here? Plus 2. What was over here? 1 minus x. Did everybody have a 7 there?
I had 3.
All right, give me somebody that had a 4, because that's very similar to the one we did last period. So with 4 minus x, what? If you had a 4 here, what was here? A what? 2? And this is still 1 minus x? When we have, and this is what I hate about problems like this, the way I wrote this, it's kind of ambiguous whether that 2 should be underneath or not, so it's not underneath. Okay. What do you how do you get rid of radicals? Square. If they're root 2, you square them. If they're root 3, you cube them. Root 4, you raise them to the 4th power, that kind of stuff, right? So you're going to use that opposite or inverse operation. But can I do that right away here? No, I can't. I have to isolate it first, okay? And this is the logic behind why we have to isolate. Remember, we want to go from step to step and hopefully make things a little bit more simpler looking, right? Okay. But if I start just squaring this side right away, okay, that means I got to FOIL that, right? So kind of visualize first times the first. These two things will be multiplied together, right? Okay. Well, when I multiply a radical by itself, I just get the radicand, right? Like radical 3 times radical 3 is just 3. So radical 4 minus x times radical 4 minus x is just 4 minus x. And that's nice. Got the radical go away, right? When I do last times last, I'll get 2 squared, which is just 4. That's awesome. No radical yet, right? But when I do O and I, okay, this will be an outside, and this ends up being an inside, okay? Or maybe I phrased that wrong, but when I multiply those two things together, this route, 4 minus x plus 2, radical 4 minus x plus 2, I'm going to take that one times that one, right? Okay, that's my outsides. And then my insides are going to be those two, right? When I multiply those together and add them up, I get 4 radical 4 minus x. So the whole thing, the whole procedure, the squaring, was intended to get rid of the radical, right? And it did get rid of it somewhere, but it introduced it again somewhere else, right? So that's kind of maybe a futile process. It didn't really gain us anything, okay? You weren't wrong. You can do that. As long as we do it to both sides, you're fine, right? But it didn't get down to something a little bit simpler. So hopefully if you do that, you recognize that. So I shouldn't do that. And I'll go back and try something else. So the other thing that we want to try is to isolate that. Get that by itself. So we go radical 4 minus x is equal to, subtract your 2, so it'll be negative 1 minus x. Now we can square both sides. Now we'll get 4 minus x on this side when we square it. This side will get negative 1 squared is 1. Negative x squared is x squared. And then when I multiply those two things together, it'll be 1x. And then I double that to give me my O and I added together, right? Okay. You guys remember doing that in this Coles class last year? If I have a plus b squared, that is a quick way of evaluating that or expanding that. Square the first term, square the last term, and then I add those together and double it. So it gives me 2ab. Okay. Which is what I did here. I multiply those together and double. And that's because that's my O and I. And if I had a plus b, multiply outsides, you get a and b, right? A times b. Multiply insides, you get a times b. Well, a times b plus a times b is 2ab. Okay? So that's kind of a shortcut that we use to expand things a little bit faster. So now we're going to solve for 0, right? Or get x squared plus my whatever x term is plus my constant is equal to 0. So just moving some things around here. We'll have x squared. I'll move my x over, so it gives me 3x. I will move my 4 over, so it gives me negative 3 is equal to 0. You guys agree with that? All right. Now, are there two numbers that you can think of that multiply together to give me negative 3, but have to give me positive 3? Huh? No. Okay. So if that's not the case, what do you have to do? Quadratic formula. So we're going to say x is equal to the opposite of b. Okay, so it'll be negative 3 plus or minus b squared minus 4ac all over 2a. So negative 3 plus or minus 9 plus 12, right? 21. And then 2. 21 is not reducible, right? Okay. Just a quick thing real quick. We talked about this in last class. When we want to reduce these, okay, like radical 21, remember what we're trying to do, and we've done the prime factorization, all that kind of stuff in previous courses, but what we're really trying to do here is see what does, or what is the largest perfect square that will divide 21, okay, and give me a whole number back, okay? Well, think about the first whole number that you can get back through any division, okay? Take 21. I can divide it by 21 and get 1, right? That doesn't really give me anything interesting, okay? What can I divide 21 by to get 2? 10.5, right? It's the only way I can do it, okay? So my perfect squares that may reside in here that's going to at least give me a 2 back, something that's interesting, are going to have to be less than 10.5. So when I'm checking if that is divisible, my perfect squares that are less than 10.5 are 1, but 1 is trivial. We're not going to check that one. 4 and 9, right? Did 4 and 9 divide 21? No, so it's simple. Okay. We did 125 a little bit ago. If I had radical 125, okay, I'm going to look at half that number, about 62, right? 62 and a half. Okay. Well, now I'm going to look at the perfect squares that are less than. Okay. Which is about 5 or 6 of them, right? And I find out that 25 is the largest perfect square that is less than 62 and a half. That divides that number evenly. Give me a 5 back. Does that make sense? Okay. So that's kind of the quick way, or a quicker way than saying, okay, I'm going to take 125, break that down to 5 and 25, and then 25 goes to 5 and 5. Pair those up, make that come outside, leave the radical 5 underneath. Okay. So these are my solutions that I think work. Okay. Or at least those are the solutions to this, right? But remember, this was ultimately a different graph. It's a different equation than what we started with, right? Okay, what we started with here in green. What we need to understand is that when we develop this one, okay, all the solutions of the green one are solutions for this red one, okay? But all the solutions for the red one may not be solutions for the green one. So we've got to check these things. And I think the easiest way to check these things is to go y equals. Okay, and I'm just going to type in this equation, but I'm going to manipulate it a little bit. I'm going to get this right-hand side to be 0. Okay, so I'm going to type in 4 minus x underneath the radical, plus 2. I'll subtract 1 from both sides and then add x to both sides. That kind of makes sense? I'll get my right-hand side to be 0. All right. The next thing I'm going to do is I'm going to go to second, hit my window key. It's going to take me to the table set functions or the table setup. And I want to go down to the independent variable and make sure ask is highlighted. Okay? Because that tells me some specific values. Or I'm allowed to ask it specific values. Notice if I go to auto, somebody in the last class had this question. If I leave it on auto, I'm going to go to my table here in a moment. But notice how it automatically fills my table, right? Well, these numbers right here are not going to be these numbers that we found down here. Does that make sense? There's other ways you can get these things to change. Okay, if I go table set and I change it, they were increasing by 1s. You know, I could get it to increase by like 1/4 if I wanted to. But hopefully you realize that's going to be really hard to figure out how to encapsulate that set of values by changing these. Does that make sense? Okay. So the best thing to do, I always leave my table set, my independent variable, I always leave on ask, because now it gets me back to this. And now I can tell it which x values to look at. All right. I'm going to plug in -3 plus square root of 21 over 2. Hit enter. And it did not give me 0 back, right? That's an issue. So -3 plus radical 21 over 2 is not a solution. Okay? I want to check the other one just to make sure. Got my parenthesis. We'll talk about the parentheses here in a minute. Parenthesis -3 minus square root of 21 divided by 2. That one does give me that 0 back. So that one does end up being a solution. Does that make sense, everybody? Make sure that we understand why I had to put parentheses in there. When we do this, we want that sum up top to be calculated first, right? Okay. Now we write things by hand a little bit differently than the way we type them in. But when we type them in, I want to make sure that -3 plus or minus radical 21, I want the calculator to calculate that first and then divide by 2. Okay? I see way too often people do this. -3 plus radical 21 divided by 2. If I eliminate parentheses like that, the calculator understands PEMDAS, please excuse my dear Aunt Sally, parentheses, x1 multiply, divide, add, subtract, very well. Okay, it never messes them up. Okay? And what would it do there first if I typed in as that red statement about multiply and divide comes before add and subtract, right? So it's going to do this first. Okay? And then it's going to add -3 to that. Okay? Which is not the same thing as what we got going on here, the same thing we got going on there. Right? So parentheses are a very, 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 very big component for plugging stuff in. Okay? There are other ways to use the calculator to check that. That's just one. But as we go through the year, you'll see other ways of being able to calculate things and check things with your calculator. There's probably about 3 or 4 different substitution techniques that we can use on our calculator to check our solutions. And that's all that is. Hopefully you guys realize that's all that is. We're taking that equation, okay, and I'm telling it which x values to plug in, which x values to substitute into that equation, and it's providing me then the output, okay, and we want an output that is equal to 0, and that then tells us that we're good to go. Is that okay? Okay. A couple other ways of doing that, and we'll get to those later on in the year. I want to stop right there.